Okay, let me click that OK up there. Where'd my mouse go? Here it is. Okay. Okay. All right.
Hello, everyone. Welcome to this week's MLOps Ideas MS series. And it's our honor to invite Dan Fu from CS Department of Stanford to give a talk today. And Dan Fu is co-advised by Christopher Lee and Kevin Betahalian. His research interests are at the intersection of movement. Recently, he has focused on developing algorithm architectures to make machine learning more efficient, especially for enabling longer context applications. His research has appeared as oral and spotlight presentations at years ICML and iClear, and he has received a best student paper runner-up at UAI. Then has also been supported by an DFEG fellowship. And thank you, Stanford, for coming, and now I can take it on.
Well, thanks. I was just trying to make it so that you don't hear that chime every time someone logs in, but hopefully it'll be okay. All right. Thanks so much for having me today. My name is Dan. I'm a PhD student at Stanford. I'm just really excited today to talk a little bit about my research on what I like to call hardware-aware efficient primitives for machine learning. So this will be a pretty casual talk, so feel free to interrupt me with questions or anything. I'll also pause a couple times for questions throughout the talk. I'll apologize ahead of time. My voice has been a bit croaky the past couple of days, so if my volume goes down progressively throughout the next hour, apologies ahead of time. Hopefully, those of you in the back will be able to hear me okay. Yeah, so in this talk, we're going to be kind of looking at alternative architectures to for things like language models and machine learning. And we'll be looking at also the systems aspects of how to make them really efficient, wall clock efficient. Before we get started, there's basically 3 ideas that I hope you will take away from today's talk. So first of all, when we're developing these new machine learning architectures, these alternatives to transformers, one thing that I hope that you take away is that in that process, it will be really helpful and really useful to develop really simple synthetic languages to do that development instead of doing something like training a model and then trying to train a big language model to see if it works. Instead, what I hope to impress upon you is that it's just really useful to construct a really simple synthetic language to try to understand what's going on more deeply. Second, the second part of the talk, we'll be looking at the systems aspects of things. And here the key idea is something I like to call 20th century algorithms, 21st century hardware and applications. What that means is that as we're developing these new machine learning techniques and as hardware is changing, we actually need to go back and take a second look at classic algorithms like the FFT, the Fast Fourier Transform, and see that we actually have to compute it a little bit differently. And thirdly, in the third part of the talk, I hope you'll see that these 2 ways of thinking, this kind of machine learning way of thinking and the system way of thinking, they're not separate modes of thinking, but they're actually quite deeply intertwined with each other. And that the insights that you develop, say, in systems can inform the machine learning primitives that you want to develop and vice versa. With that, let's go ahead and jump into the talk. I'll start with some sort of high-level motivation of some of the exciting progress that we've made in machine learning over the past couple of years. Today, you can go to ChatGPT, ask it to generate a creative poem or debug the code for you. You can do these text generation and understanding tasks at your human level, which is quite exciting. You can go to a service like Midjourney and ask it to generate beautiful pictures and landscapes. It can generate these images very well. Perhaps most excitingly, these advances in machine learning are starting to make their way to the sciences. So with models like AlphaFold, there's hope that these could really change our approach to the sciences, change our approach to things like drug discovery. My research is interested in the question of what has made these advances possible and how can we improve on them for the next generation. So one clear driver of these capabilities has been scale. And by scale, oftentimes we think about scale in terms of model size, model parameters. Over the past few years, we've gone from small 100 million parameter BERT models, relatively small 100 million parameters. Today, the best parameters are 500 billion parameters, 1.8 trillion parameters. So these, as we scale these models in parameter size, you've seen a lot of these new capabilities like human-like chat capabilities, ability to write code, some of the amazing things that we saw in the previous slides. But there's another axis along which we've started to scale these models. This is something that we call context length. What that means is how much input can one of these models take in one go, and how much input can you use to actually make a decision or make a prediction? A few years ago, the best models like BERT, GPT-1, they could only take maybe 100 tokens, 512 tokens of text. In text, that's about 1 page of text. So if you wanted to do something like analyze a whole book, you'd have to split the whole book up into individual pages, analyze each page directly, and then try to aggregate the results. And clearly, when you're reading a book, you don't just read it 1 page at a time. So there are clear limitations to that. Today, the best models have scaled to context lengths around 1 million. That means there's some practical capabilities. You can now upload a whole PDF to ChatGPT instead of splitting it up. You can start to learn from whole books or high resolution images. But the other reason it's really exciting is that it's starting to enable new long context modalities like DNA analysis straight from the base pairs, where the human genome is about 6 billion base pairs long. So if we want to do something like try to analyze the whole human genome, we want to continue to push these context things further and further. Similar story for video. This model can now analyze about an hour's worth of video. If you want to do it at higher resolutions or longer context or even longer videos, say a whole day's worth of traffic footage or something, you really want to start pushing further on context length. The basic observation and thesis of my research is that efficiency is increasingly tied to quality in machine learning. So that can mean that you have a more efficient training pipeline, so you can train a larger model over more data, or you're more efficient context length, so you can start to enable some of these new modalities. So the question that we'll look at in this talk is how can we improve the efficiency of the core primitives in machine learning? What do I mean by core primitives? This is a basic kind of diagram of a transformer. And a transformer is really composed of 2 basic building blocks called MLP and attention. So these building blocks are great. They led to a lot of the advances we saw in the previous slides, but both of these building blocks scale quadratically along one of these axes that we really care about. So the MLP, this scales quadratically in the model dimension, the hidden dimension of these models. Attention scales quadratically in the context length of these models. So how can we actually make these basic building blocks more efficient? My research takes a mix between a machine learning and a systems approach to this problem. On the ML side, the question is, how can we make more efficient machine learning algorithms? How can we change those basic building blocks themselves? So here you'll see that the core ideas will be taking inspiration from ideas in signal processing, thinking and reasoning in terms of the asymptotic big O scaling of these algorithms, using synthetic examples to try to understand their basic capabilities. On this side, I have worked in data efficient training, training with less labeled data or weaker forms of data like supervision, and improving the basic loss functions that we use to train a lot of these models. On the system side, the question is, so we think a little bit differently, and the question is really, given a particular machine learning algorithm, how can we improve the wall clock or the memory footprint of these algorithms by making them hardware aware? So here you'll see that the key ideas are going to be things like tiling or scheduling, or using kernel fusion, roofline analyses to try to understand what are the key bottlenecks and reasoning in terms of things like the I/O properties of a particular algorithm. So here I work in fast systems algorithms for training and inference of key machine learning primitives. And in today's talk, I'm not going to focus so much on either end of this Venn diagram, but really I'm going to try to focus on the intersection. This is what I like to call hardware-aware efficient algorithms for machine learning, or efficient primitives. So this is both when we're going to be changing the basic building blocks of these models, and also at the same time developing the hardware-aware systems algorithms to make them efficient. I'll also briefly note that throughout my work, my research has been inspired by key applications, whether it's DNA modeling or video analysis. I'm not going to focus so much on those applications in today's talk, but when one of those key applications comes up, I'll just try to flash up this little circular symbol up to kind of indicate one of those key motivating applications. I'll briefly note that we've been very fortunate that this style of work, this mix between machine learning and systems, seems to be resonating with the community. So a lot of the ideas and techniques that you'll see in this talk have been getting quite a bit of adoption in industry, which we're quite excited by. With that, so this talk will be split into 3 parts. So the first 2 parts are actually going to take the bulk of the time And they're going to be focusing on this attention block here. So we're going to be asking the question, how can we replace this attention block with something that can scale sub-quadratically in the sequence length? First, we're going to put on a machine learning hat and look at what primitive can we use to replace attention in language modeling. We'll see how we can use state-space models to replace attention for language models and figure out how to make them more performant. Then we'll put on a systems hat and ask the question of, okay, given that we have this new emerging class of primitives, how can we make it hardware efficient to improve the wall clock runtime of these algorithms? Then in the third part of the talk, we'll switch gears a little bit. So we're not only going to be looking at the attention block, we'll also look at the MLP block as well. And the other way that we'll switch gears is that instead of looking at machine learning systems separately, we'll actually look at them both at the same time. So at the end, we'll kind of combine them and look at this third paper. And at the end, I'll also talk a little bit about the future directions of future work that I see that I like to continue pushing on to push this boundary of machine learning systems. All right, so with that, let's go ahead and dive into the first part of the talk and look at what primitives can we use to replace attention in key applications like language modeling. And the key idea, as we start this section, the key idea is going to be we're going to use really simple synthetics to try to understand the key capabilities of some of these primitives. And we're going to be able to use them to understand complex learning problems like language modeling. All right. Second. All right. And the primitive that we're going to be looking at in the section is going to be this one called state-space model. So let me first paint a picture of why we got interested in this set of primitives a few years ago. So if you're not familiar with state-space models, they're exciting for some computational reasons and also for some kind of modeling quality reasons. So from a computational perspective, a state-space model, you can think about it as this mixture between a convolutional neural network and a recurrent neural network. The reason that's exciting on the convolutional side, they can train it in n log n time using the convolution. And then during inference, you can get very fast, basically roughly O1 generation of sequencing. So you have this nice sub-quadratic scaling in terms of the sequencing. But it's not just that. It's not just these nice computational bits. The other reason that we were excited about state-space models is that there was increasing evidence that they were a really strong general-purpose sequence. So a couple of years ago, these state-based models were starting to get state-of-the-art performance in things like audio generation or speech generation straight from audio waveforms, time series analysis of things like brain EEG signals. And so they were setting, we're getting these really nice quality results. Our basic question was, okay, we have this new high quality primitive that scales sub-quadratically. Can we get it to work for language? There was just one problem, which is that when we actually went and looked at this, we found that state-space models had a huge gap to attention in terms of quality on language modeling. So here I'm showing you a metric called perplexity. And in this metric called perplexity, lower is better for language modeling. I'm showing you the performance of a transformer compared to two models where we replace that attention block with SSM. So that's what the S4D and this GSS stand for. You can see that there's almost a 5-point perplexity gap here. So what does 5 points mean? 5 points is roughly the gap between a 125 million parameter model and a 7 billion parameter model. So what I've done here is I've just taken two models of those sizes and asked each of them, who is Alan Turing? You can see that the smaller model is hallucinating that Alan Turing is the co-founder of Ethereum, whereas the larger model can correctly identify that Alan Turing was this influential mathematician with groundbreaking work in cryptography and computer science. So this gap in quality is actually pretty big and pretty catastrophic. So our goal was, okay, can we try to understand and close this major quality gap here? I'd like to tell you a little bit about my general approach to developing new primitives like this. So first, when we identify a promising primitive like state-space models, the next step is we want to try to deeply dive in and understand the major use case. In this case, it will be language modeling. Once we have that basic understanding, instead of doing something like tweaking the primitives and then training a bunch of models, kind of boiling the oceans, using all the GPUs available on the planet to try to random walk our way to a better solution. Instead, what we're going to do is we're going to build a really simple synthetic language to try to understand this gap here. And in this case, we're going to put together a simple synthetic called associate recall. That synthetic is going to allow us to understand not all the aspects of this complex use case, but rather it will allow us to understand just one key aspect very deeply. And then using that understanding, using that insight, we'll be able to go on and develop a new solution. In this case, we'll be looking at a layer called H3, basically a gated state space model. And then using those insights, we'll be able to go back and kind of solve the original problem that we were really excited about. So let's go on now and try to deeply understand this use case of language modeling. I'll just give you a basic tutorial, basic run through of transformers and how transformers do language modeling so that we can understand some of their key aspects. The basic conceit of a transformer is you're going to take your input and split it up into a series of tokens. So for language, for example, you can have each word have a unique token. And in language modeling, what you're going to do is you're going to try to say, okay, given a particular input, try to predict what the next token is going to be. So you can see here that I just put together this really simple example here. Barack and Michelle Obama went to Harvard to visit their daughter. And the hope is that the language model will have seen enough data during pre-training to know that the Obamas have two daughters. One of them went to Harvard, and the daughter who went to Harvard, her name is Malia. So we'll be able to kind of put all these context clues together to predict that the next word should be Malia. The way that a transformer will do this is that it will compare every input, every token in the input to every other token. So I've just briefly animated this here. You can see that for each orange dot that comes up, you have to do a dot product, a comparison with every token that comes before. And so this is why you get this quadratic scaling. You can imagine that as this vector gets very long, you're going to have a lot of compute. It's going to grow more expensive. But the reason that it's useful is that when you're trying to predict this next token, it's useful to go back and compare, do a dot product between daughter, Barack, Michelle Obama, Harvard, to try to put together the context clues of who we're trying to talk about. But once we have this basic understanding, how can we improve this scaling? How can we go from this blue quadratic curve down to one of these red or orange sub-quadratic curves? And so our approach here is we're going to try to construct a simple synthetic that can capture this basic interaction to design a better layer, a better model. We put together a couple synthetic languages. I'll just go into one more deeply here, and one that ended up being particularly informative for us. This is a really simple synthetic called associate recall. It's a really simple task. There's a vocabulary of, say, 20 tokens. It's kind of a key value lookup task. So some of the tokens will be keys like A, B, C, and D. Some of the tokens will be values like 1, 2, 3, and 4. In each sentence, you have a particular mapping of keys and values. And the task is really simple. At the end, you have a key that doesn't have the value associated with it. All you have to do is go back and look up what is the correct value that you should be predicting here. So this is a really simple task. You can probably solve it with 5 lines of Python code and a hash table. But the reason that it's really useful is that it just captures just one key aspect of language. So it doesn't capture all the aspects of language, it just mimics this one key aspect, which is that when you're trying to predict this next token, it's really useful to go back and look at some of the previous tokens that came before, kind of bring them forward to do that prediction. And the surprising thing is, even though this was a really simple task and state-based models were setting these state-of-the-art performance in all these different settings, we were noticing a huge gap between state-based models and attention. So here I'm showing you accuracy of just that next token, the last token prediction. So here, higher is better. And again, I'm showing you the performance of transform against 2 SSMs. So here, I'm showing the performance of 2 really simple models, kind of 2-layer models. So really small, really simple, really easy to analyze. You can see that the transformer can solve this task perfectly, whereas the SSMs really lag behind. So it's not only that, so kind of have this puzzle that we have this SSM primitive that is super powerful in all these sequence modeling tasks, but somehow it can't solve the super simple task. So what's going on here? So what we did is we literally sat down and tried to write out by hand, manually write down by hand, the weights of SSMs to try to solve these tasks in different settings. So I'll try to animate this for you and show you kind of what that looks like. So here I've taken this example from before. I've just done something really simple. So I've gone and assigned a unique real number. I've assigned a real number to each token in the vocabulary, kind of an embedding of the vocabulary here. And what we're going to do is we're going to try to write out SSM weights in this layer to try to get the right answer. So the way to think about this is that this blue curve, this is kind of a convolutional signal processing view of the SSM weights. And this green is going to be the output here. So what I've done here is because the answer that we want is ultimately going to be 1, just assign a very kind of sharp negative value to this so we can very easily visualize when we get the right answer. This green curve is going to be the output of this layer. And the first thing we're going to find is that we actually are going to be able to write out SSM weights by hand that can solve this particular example. So you see that this green dot here matches exactly this orange dot. What that means is that this SSM layer is correctly predicting that the next token should be 1. And the way that we can do this is pretty simple. We can write out some pretty simple SSM weights. So you can see this is a pretty simple filter. Most of the values are 0. We just have this one spike here. And when you take this orange curve and convolve it with this blue curve, you get this green curve as the answer. And you can see that we actually get the right answer here. So our first result, go ahead. Is this embedding supposed to be continuous? Technically it is. So these orange dots are kind of real numbers, but it's continuous up to 32-bit precision, if that makes sense. So it's just real numbers, but in the machine learning sense of real numbers. Yeah.
But so if it's continuous, then how do we know the green of the of the orange embeddings where the token is on?
Yeah, so like if you look very, very closely at this, you can see that the green is slightly lower than this orange, but you can imagine that what the model is going to do is it's going to like find do a softmax or something of and find the closest token to this. So you can see that this orange dot is closer to this green dot is closer to this orange dot than the others. And there's only, in this case, 8 tokens to choose from. So you find the token that is closest. Yeah. And sorry, for those on Zoom, I'll try to repeat the questions. The question was about the continuity of the embedding space. Yeah, so continuing on, our first conclusion was that given a particular example, you actually can write out SSM weights to solve this problem exactly. So that was the first conclusion. The only challenge was once you've written out these weights by hand, these blue weights by hand, this exact same set of weights has to work for any example that you want to give it. So I can do something as simple as just switch around the order of the C and the B in this sentence. And you can see that we still have the C at the end, so we should still get the same answer. But when we run this exact same system forward, we are now getting the wrong answer. So you can see that this green dot at the end here is no longer matching this very negative orange dot here. And the reason is that because we wrote out the SSM weights by hand and this filter is kind of fixed in the model weights, we can do something like a static lookup of these SSMs can do things like static lookups of, say, pick out the token that came 10 tokens before, the one that I saw 12 tokens ago. But the static weights cannot do something like dynamically look up something that came, dynamically look up something based on some last token. So we can't say, look at the C token and then look up the token that came the last time we saw the C. So we kind of struggle to do these very dynamic lookups, which of course you need to do in this task because you don't know how many tokens ago it was that you last saw a particular key. But now we have a relatively simple technical challenge that we can try to solve. And if you think about this deeply, you can kind of start to imagine all sorts of ways that we can try to solve this problem. I'm just going to show you one way that we did it in this work, what we think of as the simplest delta between a standard SSM layer and and what comes next. And of course, people have come up with better or more complex ways to do this since then. But the simplest fix that we came up with is just something called element-wise gating. The way to think about this is that these circles with dots, these are just element-wise multiplication of two vectors. And this is going to allow us to do some of that dynamic selection that we needed for this associative recall task. I'll walk you again through kind of one way to do this using this element-wise gating. So first, there's a bit more going on here, but I'll just walk you through kind of what each of the steps does. So first, I know that, again, we're going to get the right answer here. So notice that the green dot at the end exactly matches this orange dot here. So first, notice, so there's going to be 3 branches in this layer, and each branch is going to kind of convey some different information here. So this first branch, you can think of it as just passing forward the token embedding that we saw before. So exactly the same mechanism that we saw in the previous slides. The second branch, this is just going to act as a really simple indicator function. All it's going to do, is it's just going to check whether the previous token that we saw is the C token. So you can see that because we saw the C here, on the next time step, we have this spike here. So if you take this orange curve and do an element-wise multiplication with this purple curve, you now get if you take these 2 orange curves and do an element-wise multiplication, you now get this purple curve. So notice what we've done here is we have successfully extracted the value of the embedding of the 1 token. So you take this purple curve, and now this SSM filter, this is a really simple filter that's going to act as basically a global memory store. You take this purple curve convolved with this blue curve, and now you get this other purple curve. So now notice what we've done. So we have successfully memorized the value of the embedding of the 1 token for the entire sequence. So you can see that this very negative value we've now successfully carried on for the entire sequence. Lastly, in this last branch here, all we're going to do is, again, we're going to have a really simple indicator function of whether the current token that we're seeing is the C token. So you can see that there's just these spikes here when we see the C token. But if you take this purple curve, do an element-wise multiplication with this orange curve, you now get this green curve at the end, which has successfully outputted the value of the 1 embedding, but only in the cases where we see the C token. You take this exact same system and do something like change around the order of the tokens as we saw in the previous slide, or in the last example, run forward again this exact same system. We're still getting the right answer here. So we're still getting this green dot is matching this orange dot. Or you can change the mapping of keys to values, and again, run forward this exact same system. And here you can see that this green dot still matches the orange dot. The basic, go ahead, question?
Not sure what the significance of the font is on K. So are you like applying a convolution on K?
Yeah.
Using
So that's just let me go back. Yeah, so that's just a really simple thing to do. So notice that this is an indicator function of what the previous token is. So the way that you actually encode this is that this K is actually the exact same thing as this V, except then you're just gonna, the short convolution is just gonna shift everything over by 1. So technically, this K has the same value as V, but then the short conv just shifts everything by 1. The actual value of that is like 0, 1, 0 or something like that. But yeah, great question. So the basic intuition here is that these gates are allowing for a very simple selection mechanism, where this first gate is saying selecting which embeddings are we going to store in this global memory of this SSM. And then the second gate is just selecting when are we going to take the value in that global memory and extract it, send it forward. We can prove that this simple layer here can solve the associative recall problem with parameters that scale linearly in the size of the vocabulary, or later on with a smarter mapping from vocabulary to the embeddings here, we can actually get sub-quadratic scaling in the vocabulary size. It's not just that we can manually write out the weights here. We can also train models that can do this.
So here we take this exact same experiment before with these simple two-layer models. You can see that this H3 model can nearly close the gap to transformers. We can also then go on and take this simple layer and scale up models up to kind of full-size language models. So here we scale up to 3 billion parameters and train it on 300 billion tokens of text. You can see that in these cases, these H3 models can match transformers, the best transformers of the day, on upstream training metrics like perplexity. So here I'm showing you perplexity again, or on downstream metrics. So you can take these models that we fully trained and evaluate them on things like zero-shot, few-shot performance, benchmarks like superglue, and we can match in zero-shot, few-shot performance here. And remember at the beginning of the section, I told you that SSMs have this convolutional and recurrent formulation. What that means is that we train these models convolutionally. Then during inference time, we can do very fast O1 generation that allows us, in this case, to get up to 2.4 times faster generation of SSMs compared to transformers. Go ahead.
One very quick question. So I understand that H3 should be faster because you use the SSM, right? But why? So I just want to know whether you have any intuition about why, given the same number of parameters, why the H3 outperforms transformer
in quality?
Yeah.
Okay, yeah. So that's a great question. We have some anecdotal evidence and a little bit of we've started looking into it with some kind of deeper error analyses afterwards. It seems that the SSMs are generally a little bit better at memorizing facts in transformers. Like they will pick up facts a little bit faster than attention. We don't really have a great mechanistic understanding of that yet because nobody really understands how a language model memorizes a set of facts. But that's generally the feeling that we get. When you kind of chat with these models, you get a little bit smoother conversation. Like they seem to carry forward the topics of conversation a little bit better than transformers. But that is a very anecdotal vibes-based analysis. So we don't have a super great understanding. But maybe it relates to all those things that we saw at the beginning of the section on like the better general sequence modeling capabilities. That's our best understanding as of now.
Oh, that's helpful. Thank you.
I'll tell you a little bit about how these ideas have evolved since we put out this work a couple of years ago. So people have taken this idea of synthetics and pushed them forward. There's more complex versions of associative recall that try to capture more bits of language modeling. There's one called multi-query associative recall now. At some point, we got interested in BERT-style models. And so we put together a bidirectional version of this associative recall task where the answer actually comes later in the sequence. The architectures themselves have evolved, where we figured out that you don't necessarily need all this SSM infrastructure to train these models. You can actually train them convolutionally. Of course, we took the BERT-style synthetics and used them to train up some BERT-style models. And if you're familiar with more recent work like Mamba, basically they take these intuitions that we developed with associative recall that you need to do these selection mechanisms. And in addition to gating, also built in some more selection mechanisms within the SSM parameterization themselves. As one cute little demo, one cute example of how this work has evolved, this is a model called Striped Hyena that was trained by some of my colleagues at Together AI. Basically, you scale the model up to 7 billion parameters and you do some conversation tuning. And last night, when I got into my hotel, I asked it, hey, I'm giving this talk at UW-Madison tomorrow to this idea seminar. What's something nice I can say about the university and the campus? You can see that it generated this very nice information about the university's strong reputation for academic excellence, the department's strong focus on innovation, and Madison's vibrant arts and culture scene and its historic landmarks, high quality of life, make it an attractive place to live and work. I'll let you guys be the judge of how nice that is. But also your beautiful, diverse architecture on campus, your well-maintained green spaces, and your numerous opportunities for recreation and engagement. It's not just language where these ideas have shown some promise. With my colleagues at Together in collaboration with the ARC Institute, took this basic H3 model, again, scaled it up to 7 billion parameters, and this time trained it straight on DNA from base pairs. And they were able to train these DNA models and then use them to generate proteins and RNA sequences. I think jury is still out on whether these are useful biologically, but at least they're showing some basic promise in learning some basic structures about these data. And as we bring this section to a close, I just want to kind of conclude by briefly calling out that the main idea here is that when we are trying to develop these new primitives, these new ideas, it's really useful to develop really simple synthetic languages to try to understand some of the complex learning dynamics. And with that, I'll briefly pause for a question or two. All right, I'll move on to the second section. Sorry. So here in this part, we're gonna take a more of a hardware, a systems approach, put on a systems hat for this section. In this section, what we're gonna be doing is we're gonna try to improve the wall clock time of some of these new primitives. And here the main idea will be, as we're developing these new machine learning primitives and as hardware is changing, again, we need to go back and look at how we compute some classic algorithms like the FFT. Some algorithms that have been around for 60 odd years at this point, but turns out as things are changing, we actually need to compute them quite differently. The motivation here was that there's this, there's these new emerging classes of models called broadly, we call them long convolutional models. They include SSMs, but also models like Hyena, RWPV, a model out of Meta called Mega. What all these models had in common is that they were getting state-of-the-art these long context applications, and they all scaled in n log n in the sequence length using the FFT. And the way that they all worked is that instead of computing the convolution using like PyTorch conv1d, excuse me, like you would naively implement it, instead they use something called the FFT convolution. So you take an FFT of your input and your kernel, do pointwise multiplication, and then take an inverse FFT. And because you can compute the FFT in n log n time, this ultimately makes the entire convolution have n log n performance. If you're familiar with the FFT at this point, you're probably thinking, okay, great. So the FFT is probably the most optimized operation on the planet. It's got this nice n log n divide and conquer algorithm that I learned about in class or from YouTube. People have called it the most important numerical algorithm of our lifetime. It's got applications in signal processing, control theory, and a lot more. I bet the folks at Nvidia have optimized, have really optimized this algorithm. It's going to run super fast. Unfortunately, when you actually try to run some of these algorithms, that's not quite the case. So here I'm showing you the runtime of flash attention in red compared to FFT convolution on an A100 using Nvidia's fastest cuFFT libraries. You can see that for the very long sequences, the asymptotic scaling takes over, but for short sequences, the FFT convolution is actually even slower than flash attention, even with the most optimized Nvidia vendor libraries like cuFFT. So our goal was, okay, how can we actually realize that this nice asymptotic scaling, even for the short sequences, can we make the FFT? Oh, sorry about that. Let me display button again. Okay, can we actually make the FFT convolution fast? I'll briefly tell you how I like to approach systems problems like these. So first, once we've identified a promising new primitive, I like to try to analyze the hardware, try to understand what are the key bottlenecks. Using that understanding, we'll go and develop a new solution. In this case, we call it FlashFFTConv. We'll use that new solution to go back and speed up the original primitives. So first, let's look at those hardware bottlenecks here. There's going to be a couple bottlenecks. The first is what's called a memory bottleneck. So in modern GPUs and all kind of ML hardware accelerators, there's something called a GPU memory hierarchy. So basically what that means is that at the top of this pyramid, you have things called registers. So these are this is where the actual operations take place. So when a GPU does actual compute, the data has to be in these registers. But then you have other layers of memory like HBM. So HBM, this stands for high bandwidth memory. This is what you traditionally think of as GPU memory. When you type in Nvidia SMI, it says you have 40, 80 gigabytes of memory. You're actually looking at the HBM there. And then in between, there are other intermediate layers of memory. Things like SRAM. You can see that these intermediate layers of memory, they're much smaller, say 20 megabytes instead of 40 gigabytes. But there's a lot faster bandwidth between SRAM and registers than between HBM and registers. When you implement an FFT convolution using PyTorch and cuFFT, between each line of code, it requires a full round trip between HBM and registers. So your whole input data has to go between HBM and registers. So as a result, your FFT convolution incurs expensive I/O as sort of the first bottleneck. The first thing that you might try here, and indeed the first thing that we did try, is we sat down and we wrote a custom CUDA kernel to put the intermediate values of the FFT convolution into SRAM. So here, what we've done here is instead of taking those intermediate values and putting them on HBM, we've written a custom kernel that just puts them on this intermediate memory layer of memory called SRAM. So, but here we actually run into another bottleneck, which is that as we're trying to scale to these longer sequences, we're actually limited by the size of SRAM. So the size of SRAM is actually not big enough to hold our entire input. So we can only scale to a particular context length. So this technique called kernel fusion is ultimately bottlenecked just by the SRAM size. Surprisingly, we also ran into a compute bottleneck. And to understand that, let me walk you through this basic roofline analysis here. So this blue dot, this is what happens when you implement the FFT convolution using PyTorch or cuFFT. You can see it's under the sloped part of this curve, which means that this operation is entirely memory bottlenecked by the I/O between registers and HBM. When you do kernel fusion, you now get this orange dot. You can see it's under the flat part of this curve, which means that it is now compute bound. What's going on there is that these GPUs, they have a lot of flops available, but only if you can use specialized matrix multiply units. So on GPUs, these are called tensor cores. What they allow you to do is that they allow you to compute matrix multiply operations up to 16 times faster than general arithmetic. What that means is that if you can use the tensor cores, you effectively raise the roofline here, and you can now achieve much higher flop utilization, but only if you can use the tensor cores. What we're going to do in FlashFFTConv is we'll rewrite these FFT operations to move us to this much nicer part of the roofline analysis. So we'll get this nice green dot, get a lot higher flop utilization out of our primitives. So now let me walk you through how we use these insights to develop a solution. The idea is pretty simple. We're going to take that divide and conquer algorithm of the FFT. Instead of running it to completion, we're actually just going to cut it short early. What that's going to allow us to do is will allow us to rewrite the FFT as a series of matrix multiply operations. You can imagine that these dark blue blocks just contain the weights of the FFT matrix. So this allows us to rewrite that FFT pointwise inverse FFT operation as a series of matrix multiply operations. So these Fs are FFT matrices. The first thing that we're going to do is, of course, we're going to sit down and write a custom CUDA kernel to put all the intermediate values into SRAM. Earlier, I told you that one of the bottlenecks is that kernel fusion is limited by the size of SRAM. But here, this decomposition of the FFT, this Monarch decomposition that we call it, actually saves us again. So when we try to scale to longer sequences that don't fit into SRAM, turns out all we need to do is do one matrix multiplication in the beginning and end of the sequence. And then that allows us, basically, we're going to take that divide and conquer algorithm, recurse down one more time, split it into 3 operations instead of 2, and then we'll just have one matrix multiply at the beginning and end. Of course, this uses the tensor cores nicely, so that so we can run everything with high flop utilization, still use our nice fused kernel in the middle. And of course, the other reason that we like to use this is now we have taken these operations and we've translated all the flops to these matrix multiply operations, so we get a lot higher flop utilization. I'll briefly note that the particular way that we've written this here, so the F switch from left to right, there's some transposes here or there. This is also IO aware times one more level. So we're actually minimizing communication between SRAM and registers using the particular way that we've written out this operation here. The upshot of all of this is that we can close the runtime gap to flash attention. So here we have FlashFFTConv in green. We get up to 7.9 times speedup over Nvidia's most optimized libraries. We close the runtime gap to attention, so everything is nice and things run fast again. If you take this module and go use it for some end-to-end training, get up to between 2 and 4.5 times speedup, kind of based on how much time was the model originally spending on the convolutions. We also get some new capabilities because we're putting less things onto HBM. We actually get smaller memory usage. So we actually can scale to longer sequences than we could scale to before. Today, FlashFFTConv is used in a number of applications, from that text generation model that I showed you to some new image generation models out of Cornell Tech to some of these new DNA foundation models. And here, as we bring this section to a close, I hope you can see that how, as these machine learning primitives are changing, as hardware is changing, we actually need to sometimes go back and change the way that we compute classic algorithms like the FFT. And here, again, I'll pause for a question or two, and also drink some water, because as you can probably hear, my voice is indeed going away as we get further into the talk.
I have a question.
Mhm.
I understand how you use the matrix multiplication to like get a new line, but how do you go through the memory method?
So the basic idea is we're going to use kernel fusion, just like we did before. But the key thing about that FFT algorithm is that divide and conquer basically means for each individual matrix multiply operation, you don't necessarily need to see the whole sequence. So what that allows you to do is that in that kernel in the middle, when you're doing those matrix multiply operations, even if you have a sequence of, say, 4 million, you only need to look at some like 30,000 of the inputs at any one time. So that allows you to kind of divide and conquer your algorithm. But if you set that up correctly, that means that you just need to do one matrix multiply at the beginning and the end, and you don't need to put the whole sequence onto SRAM. So it kind of reduces the SRAM footprint for longer sequences. If that makes sense. Yeah. All right. Oh, sorry, go ahead.
And the same techniques be applied to the short time Fourier transform, which takes frames of a time sequence to make?
Maybe. So we looked a little bit into this as kind of one of the extensions of this method. So let me see if I can. Yeah, so you can imagine. So that short time FFT kind of corresponds to some basically having gaps in these matrices, so either zeroing out parts of these Fs or these things. So we looked at various ways they can sparsify these matrix multiply operations. So some of them correspond to kind of short time things, some of them correspond to kind of sparsity in the frequency domain, and different ones will have different applications, different implications. So yeah, and that's something that we're very interested in looking at, now that we have this understanding of like, this is the best way to do this FFT convolution on GPU, what new operations does it kind of open up? What other things do we want to look at? All right, with that, I'll move on to the last part of this talk. And hopefully my voice will survive for the next 10 minutes. But in this last part of the talk, like I mentioned, we're going to switch gears a little bit, kind of look at a machine learning and systems approach, and we'll also turn our attention to this MLP block as well. And the basic idea here is just you can do this the systems work and this machine learning work at the same time. And in fact, they should actually inform each other quite deeply. And to really drive that point home, these were the two cartoon diagrams of how I like to do machine learning and systems research. Really, it looks more like this, where you have a new primitive, you try to understand, does it work for your key use cases? And at the same time, you try to understand what are the key hardware implications and solutions to make them hardware efficient. The basic idea we're going to look at here is we're going to come back to this Monarch decomposition. Instead of having these dark blue blocks just be the weights of the FFT, so what we're going to do is we're going to say that these blocks can be fully learned. So from a hardware perspective, this maintains all the nice efficiency benefits that we saw in the previous slides. But from a machine learning perspective, this is going to add new layers of expressivity. So this will allow us to capture a lot more structured linear transforms, some of which I've shown you here. This paper, this work, Monarch Mixer, we're going to take this idea and run with it, try to see how far we can push it. We're going to use these Monarch matrices to try to replace both attention and the MLPs and transformers. This will allow us to scale sub-quadratically in both context length and model dimension with a primitive that is hardware efficient. This will allow us to match transformer quality with up to 27% fewer parameters, up to 9 times faster wall clock time for long sequences. This is what the basic architecture looks like. So on the attention replacement, we're going to take basically a gated SSM, replace the FFTs with these Monarch matrices. On the MLP side, we're going to take the dense linear layers, replace them with Monarch matrices or block diagonal matrices. So in our work, we can use this architecture to replace transformers in BERT-style models, vision transformer-style models, and GPT-style models. I'm just going to focus on the BERT results for the sake of time. So as exemplified by this cute little picture here, the way that you evaluate a BERT model is that you pre-train on some data, and then you try to evaluate the downstream performance after fine-tuning. So here I'm showing you the performance of 2 BERT models. Here the transformer, here the Monarch Mixer, fine-tuned on this blue data set. You can see that we can match performance in blue with 27% fewer parameters. We see a similar story when we scale up to BERT large, where again, we can match blue performance with here's 24% fewer parameters. Because we're also scaling sub-quadratic in sequence length, we're going to get a lot higher throughput. So as you scale to longer sequences, you can see that the transformer-based BERT models see this major hit in throughput, whereas the M2 models don't see nearly as huge of a hit in throughput, which results in this faster speed up over the Hugging Face models, up to 9.1 times over sequence length of 4K. Excuse me. We started to use these models to train some new long context retrieval models. So here, in some cases, these really small 80 million parameter models starting to outperform much larger, in this case, a 7 billion parameter model. So this is a model that is, 85 times larger that we can outperform because we have this much longer context length. So people have started to use these long context retrieval models. Some people have started to use them for RAG applications. People have started using these long context benchmarks to train some other long context retrieval models. So we put out this work a couple months ago, and since then it started it's kind of led to this initial explosion of new long context retrieval models that we're quite excited about. And here, as we bring this section to a close, I hope that the key takeaway here is that when you're doing machine learning and systems work, the two sides should really try to deeply inform each other, that the systems insights can inform new machine learning primitives and vice versa. With that, I'll briefly move on to the future work. Before I do that, I'll briefly mention a couple other things I've had fun working on. So the first is I've had fun optimizing transformers as well, improving training time with things like flash attention or inference times with things like FlexGen and Hydrogen. So the data matters too. So here I've put together a data set called Red Pajama with some folks at Together AI that's been used. It's a trillion token data set that's now being used to train a number of open source models. And now I'll briefly talk about future work insofar as my voice will survive over the next 4 minutes and 10 seconds. So first, we're very excited about developing new, more efficient primitives. I'm actually going to take a sip of water. So hopefully my voice can survive. really excited about developing new efficient primitives. So here I think there's a lot more to push on the MLP side. I'm thinking that there's maybe a whole order of magnitude further improvement that we can get here. Also excited in developing hardware-aware algorithms for things like Gaussian processes or wavelets, these techniques that have promising quality results, that have asymptotically efficient algorithms, but that don't necessarily have hardware-aware versions of them. On the system side, this is something I like to broadly call hardware ML systems compilers co-design. What I mean by this is that, so this is a cartoon diagram of how I do systems work. Really, there's a hidden fourth step called grad student tiers, where between analyzing the hardware and understanding the bottlenecks, between that and actually having a solution, there's a lot of blood, sweat, and tears that goes into actually developing a really efficient CUDA implementation. And so there, I think there's this nice opportunity to develop, the right compilers or domain-specific languages to try to make this process easier, more pain-free, so that between this step and this step, it doesn't take months of grad student time, but rather weeks or even days. And lastly, I'm just really excited about the long context applications of some of these new models. So we've started to see that people are starting to train these DNA models, but really the next question is, can this actually do something useful, or do we need to change the architectures more, change the data, change the training procedures? Or can you take existing models like AlphaFold and make them more efficient? So here with things like AlphaFold, you may not know this, but actually AlphaFold has a cubic operation at its core. So forget about all these sub-quadratic algorithms. Can we make AlphaFold more efficient and actually develop, say, a sub-cubic approach to things like AlphaFold? With that, so here were again the three key takeaways. For the sake of my voice, I won't say them again, but hopefully you can see how they can apply to machine learning systems. With that, I'm happy to take further questions.
For my first clarification
Sure.
question, so you mentioned the Monarch matrices as kind of sparse matrices. Am I correct? So like, so what is the, probably I missed it. So what is the benefit of it over other like sparse matrices or low matrices?
Yeah, so the main benefit is that they're very hardware efficient because they're ultimately block sparse at the core. It means you can still use the tensor cores during training. So arbitrary sparsity tends to be very hardware inefficient. Things like LoRa and stuff are very useful for fine tuning, but you typically don't try to pre-train from scratch. With the Monarch matrices, you can still pre-train from scratch, and it still has relatively high flop utilization. And that extra structure, because it generalizes the FFT, allows you to capture a lot of these operations that we care about.
Have you looked into comparisons onto other GPU vendors like the HIP and Rockwell stack for AMD?
Yeah, so we've worked a little bit with Samba Nova. They have this hardware called RDU and they've taken some of our algorithms and implemented them. We've tried to look into things like TPU a little bit. Generally, the problem that we run into with other hardware is that there's really terrible software support. So basically, our experience is that unless you work at Google, you can't develop new algorithms for TPU. Unless you work at Samba Nova and you're on the team that understands the hardware, you can't really develop new algorithms. And that's generally the pattern that we see across vendors. I know there are people who are working, especially for the AMD chips, to try to make it more general. But yeah, that's generally the problems that we run into. But in principle, and we've had like one or two cases where we've seen that it works on these vastly different hardware. But in principle, it should also work. All right.
Yeah, if there's no other questions, let's thank Danful again for
Yeah.
this great talk.
Thanks so much. Thanks so much for having me.